Welcome to Analytical Chemistry Unlocked, a short microlearning series designed for YouTube viewers who want clear, practical insights into modern analytical techniques. Over the next few minutes, we'll unpack core principles, common instruments, and emerging trends, all with real-world examples to help you connect theory to practice and improve your lab decision-making and data interpretation skills. This slide outlines the roadmap for our series, with chapters covering foundations, classical techniques, spectroscopy, chromatography, electroanalytical tools, and data handling plus future outlook. The image on the left hints at the applied, real-world labs we'll reference, and the contents list will guide our journey from basic concepts to advanced, practical workflows you can use in the field or the bench. Chapter 1 introduces the foundations and scope of analytical chemistry, so we can set a common framework before diving into methods. Think of this section as building the analytical mindset, defining what we measure and why, how traceability and reproducibility matter, and how the analytical cycle shapes method development and regulatory compliance in routine and research settings. Analytical chemistry is essentially the science of obtaining, processing, and communicating information about matter's composition and structure. And here we highlight three key applications: quality control and pharmaceutical development, environmental monitoring of pollutants, and forensic investigations. The photo of the lab reinforces that this field sits at the intersection of instruments, protocols, and careful documentation to ensure reliable, actionable results. Here we introduce the analytical cycle, a 7-step workflow from problem definition through reporting that ensures traceability and reproducibility. The graphic shows each stage: sampling, preparation, measurement, data handling, statistical evaluation and reporting, and emphasizes iteration, method, validation, and documentation, so results meet regulatory and scientific standards at every step of the process. Chapter 2 moves us into classical techniques, where time-tested, fundamental methods still play a vital role in many labs. In this chapter, we'll compare gravimetric and titrometric approaches, explore how errors are managed in simple analyses, and show how classical tools remain relevant when paired with modern quality controls and thoughtful experimental design. Gravimetric analysis quantifies analytes by mass changes, often using precipitation, volatilization, or electrodeposition, while titrometry determines concentration by reacting the sample with a standard solution and measuring volume or charge. Rather than reading every detail on the slide, think of gravimetry as direct mass-based proof and titrometry as reaction-based stoichiometry. Both reliable when sample handling and endpoint detection are properly controlled. Managing errors is central to classical analysis, and this slide separates systematic bias from random precision issues, pointing to calibration and blank corrections for bias and replicate measurements for precision. We also note practical quality control tools like uncertainty budgeting and control charts that quantify doubt, track method performance over time, and help ensure results remain within accepted tolerances. Chapter 3 introduces spectroscopic methods, a broad category of techniques that probe how matter interacts with light and electromagnetic fields. In this chapter, we'll cover molecular and atomic spectroscopy, practical strategies for UV, UV-IS, and IR work, and how chemometrics enhances interpretation when spectra overlap or samples are complex. Molecular spectroscopy relies on principles like the Beer-Lambert law for UV-HVIs and the fingerprint region for IR to identify and quantify compounds, while careful solvent choice and stray light correction improve accuracy. The illustration on the slide highlights different electronic and vibrational transitions, and we'll also discuss how chemometrics and multivariate calibration enable simultaneous quantification in complex matrices. In atomic spectroscopy, we survey a toolbox that includes flame AAS for routine major and minor elements, graphitage furnace AAS for trace detection, ICP-OES for multi-element throughput, and ICP-OMS for ultimate trace level analysis and isotope ratio work. Advanced components like collision cell technologies and internal standards underpin accurate results, especially when characterizing nanomaterials or dealing with challenging interferences. Chapter 4 opens our look at chromatographic separations, the workhorse techniques for separating complex mixtures before detection. This chapter explains core concepts like stationary and mobile phase interactions, retention mechanisms, and how chromatographic choices affect sensitivity, selectivity, and throughput for different sample types. When comparing gas and liquid chromatography, GC uses temperature-programmed dilution and carrier gas optimization for volatile analytes, whereas LC offers many modes: reversed phase, ion pair, SEC, Hillick, and relies on careful solvent gradients and retention factor manipulation for non-volatile or polar compounds. The instrument images emphasize that choosing the right platform depends on volatility, polarity, and the analytical question at hand. Detectors and method validation are where separation meets measurement, and this slide highlights universal and selective detector options and the critical ICH validation parameters. Whether using FID, UV, fluorescence, MS, or other detectors, method validation checks specificity, sensitivity, linearity, and precision, and system suitability tests ensure the chromatographic system performs reliably before and during sample analysis. Chapter 5 explores electroanalytical and emerging tools that expand capabilities for field and lab monitoring. This section looks at potentiometric and voltammetric sensors, nanostructured electrodes, and miniaturized platforms that are democratizing analysis through portability and cost-effective designs without sacrificing analytical performance. Potentiometric sensors measure potential to infer ion activity and are often used with ion-selective electrodes for pH and specific ions, while voltammetric sensors record current versus applied potential to detect redox-active species using techniques like cyclic, square-wave, and stripping voltammetry. Advances such as nanostructured electrode surfaces and refined pulse methods enable ultra-8 trace detection and improved selectivity. The miniaturized and lab-on-a-chip slide shows how microfluidic electrophoresis, paper-based assays, and smartphone red sensors are bringing analysis into the field. These platforms reduce sample and reagent use, enable rapid separations, and allow data capture and sharing via mobile devices, making diagnostics and environmental monitoring more accessible and faster to deploy. Chapter 6 turns to data handling and future outlook, where statistics, chemometrics, and digital tools translate raw measurements into knowledge. In this final chapter, we'll review foundational statistical tests, advanced multivariate techniques, and emerging trends like AI-assisted method development and greener, cloud-connected laboratory systems. Converting data into knowledge requires both foundational statistics, T-through tests, ANOVA, regression and uncertainty quantification, and advanced chemometrics like PCA and partial least squares to extract latent variables from overlapping data. The PCA plot on the slide illustrates how multivariate techniques reveal groupings and patterns that simple univariate analysis can miss, improving classification and quantification in complex samples. Looking ahead, the future of analytical chemistry is both green and digital. Greener through solvent-free and microscale methods, energy-efficient instruments and reduced waste, and digital through AIO-driven method optimization, blockchain for secure data integrity, and cloud-connected autonomous analyzers that streamline workflows and improve reproducibility across labs. Thank you for following this microlearning series on analytical chemistry. We've covered core foundations, classical and instrumental methods, error management, miniaturized tools, and data strategies for modern labs. If you'd like to explore any topic in more depth, consider the accompanying videos or resources, and stay tuned for practical demos that put these concepts into action in the bench and the field.